OEMs are constantly striving to meet strict emission regulations that apply to their vehicles. One innovative way currently employed by manufacturers is using an electronically controlled thermostat for gasoline engines. First, what is an electronically controlled thermostat? It's part of a system that relies on sensor inputs to the ECM or cooling module to manage and control heat transfer. There are numerous control maps programmed into the module, using different set points for the various driving conditions needed to activate the thermostat. So let's reflect on a conventional thermostat. They've served us pretty well up till now, but there are some limitations. Conventional types only have one opening temperature and generally start to open a few degrees before it. Because of this, the cooler radiator fluid begins to mix with a hot engine coolant too early, removing the heat energy needed for the engine components to reach optimal operating temperatures. As a result, this incurs longer warm-up times, increased emissions and fuel consumption. An electronically controlled thermostat can be opened or closed independent of coolant temperature via an internal heating element and return spring. This means the ECM can adjust the amount of coolant flow by controlling the heater within the thermostat. One of the main benefits of this technology is the reduction in hydrocarbons and carbon monoxide gases produced during part throttle applications. The ECM is programmed to maintain hotter operating temperatures under these conditions, allowing for a complete combustion event, which reduces fuel consumption. Conventional thermostats are reactive, where they open and close in reaction to the coolant they are submerged in. This means engine coolant temperatures can fluctuate more frequently, as the thermostat relies on a wax pellet to open the valve and a spring to close. Electronically controlled thermostats are proactive, meaning the ECM can open and close them based on engine speed, temperature and load conditions, achieving correct operating temperatures faster and remaining within an optimal temperature range. So let's look at two identical cars, although only one has a mapped cooling system. As both vehicles drive up a hill, the proactive type will calculate the additional heat generated from the extra load and begin to open the thermostat in preparation for the increased temperatures. Compared to this vehicle, where the thermostat remains closed until the coolant temperature reaches a preset value. By now, it's too late. The cooling system is already working harder than it should to remove the additional heat energy, placing more strain on the engine and cooling system components. The majority of conventional thermostats are located at the engine coolant outlet, whereas this new type is contained in a multifunction housing block connected between the lower radiator hose outlet and cylinder head inlet, as the temperature here is considerably less than the upper hose. It's placed in this position so the ECM has greater control to override its mechanical opening temperature. The thermostat and distribution housing are mated together. They can be manufactured from either aluminium or plastic and contain the coolant temp sensor and the heating element. These systems will generally use two coolant temperature sensors. One is used to measure cylinder head coolant temperature and the other is the outlet thermostat temperature. The two-wire heated thermostat resides in the outlet of the multifunction housing. The thermostat looks like a standard one with the exception of a heating element that is encased in a wax-filled capsule. To open the valve, the ECM will send a PWM control to the heater. The duty cycle will be altered in relation to coolant temperature, engine speed and load. The voltage supplied to the element melts and expands the wax within the capsule, acting against the lifting pin and opening the valve. When the ECM deems it appropriate, the PWM control is removed. The wax cools down and the return spring closes the valve. Looking at this cooling system flow schematic, we can see that coolant circulates within a closed circuit when the engine is cold. The ECM has a variable or proactive desired coolant temperature, so we can alter the opening set point depending on engine load, speed and actual coolant temperature. On this vehicle, the desired operating temperature under light load is about 102 degrees Celsius. With these conditions, the ECM will send a PWM command to the heating element with a duty cycle of about 2%. This low duty cycle is not enough to open the valve, but is enough to start warming the wax. As the engine temperature and load increase, the ECM will alter the heater's PWM, allowing the valve position to be reached and the desired temperature range to be maintained. We can now see on the schematic that coolant flows through both engine and ancillary circuits. If we further increase the engine speed and load, the engine coolant temperature will rise. The ECM will look to its maps and will change the desired operating temperature to a lower set point. The ECM will then increase the duty cycle control to the thermostat. As the element expands, the valve opens more and the flow of coolant meets the current engine speed, temperature and load conditions. The ECM is constantly varying the position of the thermostat, altering flow in the cooling system. To assist with higher operating temperatures that can't be controlled by the thermostat alone, the ECM will look to its cooling maps and switch the fan or fans on, helping remove the heat energy produced. When the ECM receives data that extra cooling is no longer required, the ECM will reduce the duty cycle to the thermostat heating element, changing the desired cooling temperature to meet engine load and speed conditions. As the load temperature coolant passes the valve, the wax pellet now begins to contract, and the return spring closes the valve completely. If a fault was to occur in the control circuit of the heater, the thermostat will act like a conventional type, without the aid of ECM intervention. The ECM may turn a mill on and command the cooling fans to full speed to prevent overheating. Electronically controlled thermostats are another positive step in reducing emissions, improving power, reliability and economy. Understanding how this system operates will give us confidence in the likely event we need to diagnose and repair it. Thanks for watching. See you soon.